In Unit 3, Lesson 11, we're going to be solving nonlinear systems. In this lesson, I can solve systems of nonlinear equations, and I can solve quadratic equations by graphing. So for the warm-up, it says solve the system using elimination or substitution. Check your answer with your calculator. Okay, so we've practiced using elimination and substitution before, getting us ready for this lesson. Okay, if I'm looking at this first question here, I'm probably going to use elimination to solve this one. I'm going to make the decision to eliminate the x's. So if that's the case, I'm going to have to multiply the top equation by -2 so that I get a positive 2x and a minus 2x so that that variable will drop out. So let's see, I would get negative 2x plus 8y equals a negative 18. And then I'm going to keep the second equation exactly the same. If we add those together, the x's cancel, right? We've got negative 2x plus 2x, which just becomes 0. 8y minus 3y would end up being 5y, and that's going to be equivalent to negative 7. If I divide both sides by 5, I would get that y is equal to negative 7/5. Okay, so we are not done yet. We just solved for y. We still have to get what x is equal to. So I can pick either one of these original equations to plug it back into. Let's just go ahead and go with the first equation. So instead of having x minus 4y equals 9, I'm going to replace y with negative 7/5. So I'd get x, let's see, negative 4 times negative 7 is going to end up giving me positive 28/5. Okay, and then I'll subtract 28/5 from both sides. So we have x equals what? Let's see that. Let's put that in the calculator and see what we get. So I'm going to have 9, we'll zoom in a little bit, 9 minus 28/5. You can just put it in like that and then hit math frac, which I'm just hitting the math button and then pressing enter on frac. So we end up with 17/5 for answer there. Okay, so that looks good. If I want to write my answer as an ordered pair, it would be 17/5, comma, negative 7/5. Okay. Remember, when I'm using elimination or substitution to solve, we're really finding the intersection point between these two graphs. Okay, so if you want to get each one in y equals format, you could graph them and see where the intersection is, and it should be at 17/5, comma, negative 7/5. So let's go ahead and do that just really quick. The directions do say to check your answer with your calculator. So we'll do it for the first one, just so you know what I'm talking about. Okay, so if I rewrite this first equation in y equals format, we would have x minus 4y equals 9, and I would subtract x from both sides. And then I would divide both sides by -4, which is ultimately going to give me what? That's going to give me y equals, if I divide this term by -4, I'd end up getting 1/4 x. And if I divide this term by -4, we'd get minus 9/4. So I'm going to put that into my calculator. I also need to rewrite the second equation. So we've got 2x minus 3y equals 11. If I subtract 2x from both sides, it'll look like this, and then divide both sides by -3, right? We divide every single term by -3. We end up getting y equals, that would be positive 2/3 x minus 11/3. Let's go ahead and put those two equations into our calculator under y equals and see where the intersection point is. Okay, so just in my calculator, I'm going to go into y equals, clear out what I have, and I'm going to put in those two equations. So I've got 1/4 x minus 9/4, and I've got 2/3 x minus 11/3. Okay, so I put that in. I'm going to press graph. They're both linear functions, and they do cross right here. If I want to calculate that exact intersection, We can go to second trace or second calculate, down to intersection, and just get really close to the intersection, almost on top of it, and we're going to press enter, 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 and we get 3.4, negative 1.4. Is that what this is? Let's see, what's 17 fifths, negative 7 fifths? 17 fifths, negative 7 fifths. Oops. Let's try that again. 17 fifths, negative 7 fifths. So there's our 3.4, negative 1.4. Perfect. All right, let's go over here to number 2. We're going to use substitution probably on this one because we already see that y is equal to 2x, right? Y is already by itself. So I'm just going to take 2x and substitute it in for y. 3x plus 5 times 2x equals 0. So we get 3x plus 10x equals 0. 13x equals 0. And if I divide both sides by 13, we get that x is 0. Okay, now I'm not done. I still have to figure out what y is. So remember, y was equal to 2x. So if I plug in 0 for x, we're going to get that y is equivalent to 0 as well. Okay, so my final answer, I write it as an ordered pair, x comma y, and it'd be 0 comma 0. And that's where the two lines intersect. Okay, so those were both examples with linear functions. Now we're going to work with a system of nonlinear equations where at least one of the equations is not linear or nonlinear. The solutions of a system are points where the two functions intersect. So, for example, if I look at this system right here, this would be an example of a system of nonlinear equations because we have a parabola, which is not linear, and a line. It only takes one of those functions to not be linear in order for it to be a system of nonlinear equations. Okay, when the graphs of the equation are aligned in a parabola, you can either have 0 intersection points, 1 intersection point, or 2 intersection point. In other words, the system can have 0 solutions, 1 solution, or 2 solutions. So when there's no intersection, there's no solutions. When there's 1 intersection, there's 1 solution. And when there's 2 intersections, there's 2 solutions. When we have 2 parabolas, then the graphs can intersect in 0, 1, or 2 points. So again, if there's no intersection, they would have no solution. No real solution. I should really put real, right? Because it's possible to have imaginary solutions. Okay. 1 real solution is 1 intersection point, and 2 real solutions is 2 intersection points. Okay, so in this first problem here, it says solve the system by graphing. I'm going to do this in 2 different colors. I'll go ahead and do the top one in blue, and I'll do the bottom one in red. Equation 1, what kind of function is this? This is going to be a quadratic function, right, or a parabola. So I'm expecting a parabola that opens up because there seems like there's been no reflection. Okay, and then the second function here is a line with a negative slope. So I'm going to be expecting some kind of line that goes down. Okay, so for the parabola, let's start with that. It is in standard form, right, where my a value is 1, my b value is negative 2, and my c value is negative 1. And that's important because it is in standard form, so I have to use that negative b over 2a. Okay, so to get my axis of symmetry, I'm going to use x equals negative b over 2a. Okay, we have x equals negative b. b is already a negative 2, so ultimately that's going to become a positive 2 over 2a, and a is 1. So I basically get 2 over 2, so I get 1 for my axis of symmetry. All right, let's use that to get the vertex. Remember, the vertex uses the same x value as the axis of symmetry. So I'm going to use 1 as my x value for my vertex, and I need to find y. Well, if x is 1, how do I find y? I just plug it into my equation. So I'd have 1 squared minus 2 times 1 minus 1. Right, we plugged it back into this original function up here. Okay, and now we just need to simplify. So we get y equals 1 squared is 1, negative 2 times 1 is negative 2, minus 1. we end up with what? -1 minus 1, which is -2. Okay, so I have my vertex now as well. Okay. And the last thing that I need to graph it would be my y-intercept, which for my y-intercept, remember I plug in 0 for x and I solve for y. So if I plug in 0 into my quadratic function here, we're going to end up getting 0 minus 0 minus 1. So I get 0, -1. Okay, so those are the three components I need to graph my parabola. So I'm going to graph my axis of symmetry at x equals 1. Okay, my vertex was 1, -2. So I'm going to put that right there. And my y-intercept is 0, -1. Okay, so that's half my graph. And remember, this graph should be symmetrical, so I should use the same width on the other side as well. All right, so that's the first part. The second part is I have to graph the line. In order to get my equation, or in order to get my graph, I just need to pull out the slope from my equation and also the y-intercept. So the slope here, remember this is in y equals mx plus b form, where the slope in this case would be -2, and the y-intercept would be 0, -1. So I can easily graph that. We've got 0, -1, and then I'm going to use the slope. Remember, this is rise over run. So really, I'm going to fall 2, go right 1. So go down 2, right 1, and make a point. And we're going to do that again, down 2, right 1, make a point. Okay, and we can even go up 2 from here and back 1 if I want to make another point. And doesn't it look like it's already crossing our parabola? Yeah, let me make that line a little bit straighter. Okay, where does it look like it's crossing right now? It looks like it's crossing right here, right, at 0, -1. And you can see that as well over here. See how both the y-intercepts are 0, -1? Wherever the intersection point is, that's your solution. So my solution is 0, -1, because that is the point of intersection. Okay. Normally, the only time I'll use solving by graphing for a system is with my calculator. So let me show you how to quickly make this happen in your graphing calculator. Okay, so I'm going to go into y equals. So I'm going to clear out what I have. And I'm going to go ahead and put each equation in my calculator. It's nice because they're already set in the form y equals something. So I'm going to put x squared minus 2x minus 1. See, x squared minus 2x minus 1. And I'm going to put my linear equation -2x minus 1 into my calculator. So it looks like this. I'm going to press graph. Okay, if your graph doesn't look like mine, just make sure that your zoom is under zoom standard. Okay, so like if I go to the zoom button and you go down to zoom standard, that'll get your window set like mine. Okay, and then we're looking for where the intersection point is. I can guesstimate that it's right here, but I'm not really sure where exactly it crosses. To do that, I'm going to go to second trace or second calculate, intersection. Okay, we want it to be right on the intersection. So like don't put it over here. You want it right on top of where it looks like it crosses. Press enter, 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 and you can see that we get 0, -1. Sometimes if you're not right on top of the intersection and you go to try to calculate the intersection, like if I'm over here slightly and I'm not right on the intersection, sometimes you'll get something weird like this. Like, what the heck does this mean? 8.14e negative 7, negative 1.00002. Well, this is obviously really close to negative 1, but what does that mean? Let's just talk about that really quick. I'm going to just off to the side make a note up here. Like I said, it gave us that x was equal to positive 8.1439 e negative 7, and then y was equal to negative 1.0000, etc. I think it ended with a 2. Okay, but really this is scientific notation. So this is the same thing as saying times 10 to the negative 7th power. So essentially it wants us to take this decimal point and it wants us to move it left 7. I know it's left because of the minus sign. 1, 2, 3, 4, 5, 6, 7. And then we'd fill the rest in with zeros. So what is that number really close to if I have 0.00000081439? That's going to be a number really close to 0. So we have a number really close to 0, and then we have this number really close to negative 1. Okay, let's go down here, solve the system by substitution. In order to solve by substitution, we want one of the variables by itself. So let's go ahead. I'm going to make the decision to just get y by itself. I like it in the form y equals. So let's rewrite this. We're going to get y equals negative x plus 4. So everywhere I see a y in the first equation, I'm going to replace it with negative x plus 4. All right. So we'll have x squared plus x minus y. Y was negative x plus 4 equals negative 1. Notice that when I plugged in negative x plus 4, I had to use parentheses. Okay, if you don't, it's going to screw you up. Make a note to yourself. Okay, so we'll get x squared plus x minus 4 equals negative 1. This is a quadratic equation, so I'm going to set it equal to 0 and try to factor it. We get x squared plus 2x. If I add 1 on both sides, we get minus 3 equals 0. And this is something that's factorable. If I want to factor this, what is going to multiply to give me negative 3, but sum or add to give me 2? That's going to have to be what? A positive 3 and a negative 1, right? My outers would be 3x, my inners would be negative 1x, so I'd get 2x. Excellent. Set each one of these factors equal to 0 to solve for x. So we get that x is 1, and we get that x is negative 3 when I solve for x. Okay, now I'm not quite done yet, right? I've got to still solve for y. So I've got this x equals 1, and I've got another solution, x equals negative 3, and I know that y equals negative x plus 4. So I'm going to have y equals negative x was 1, plus 4. So I get y equals negative 1 plus 4, which would be 3. So I have an ordered pair here at 1, 3. I'll do it again over here. We have y equals negative x plus 4. So I have negative x was negative 3, plus 4. You get 3 plus 4, or 7. So I'd have another solution at negative 3, 7. So those are going to be your 2 points of intersection. Let's go ahead and just check our work really quick. Plug it back into the original functions and see if it balances. Okay, don't forget to check your work. I'll do it with just one of them, but really you should do it with both of them each time. If I plug in 1, 3, this would be 1 squared plus 1 minus 3. Does that equal negative 1? Let's see, we get 2 minus 3, which does equal negative 1. Good. And then if I plug it in here, 1 plus 3 would be 4. Yes, that works. Okay. And then you'd also want to check the other point as well. You would check the negative 3, 7. Okay, in example 3, we're going to solve by elimination. We have 2 equations here. And you can see that neither of them are linear. So we are solving a system of nonlinear equations. Okay, and I always, when I'm solving systems like these, I leave whatever variable is being squared. I try not to eliminate that one. It's just going to be easier if we eliminate the variable that is not being squared. So in this case, y is not being squared. And you can see right now that if I were to just add these two equations together, negative y plus y is already going to go away. Okay, so we're going to get 3x squared. This is going to be minus 3x. The y's cancel, equal negative 2. And right there, I can see I have a quadratic equation. Let's set it equal to 0 and try to factor it. There's no GCF, so I'm just setting up my parentheses. What times what is 3x squared? That's going to end up being 3x times x. And then to multiply to give me 2, I can either do 1 and 2 like that, or I can do 2 and 1. Here we have 3x and here we have 2x. So that's not going to get me to negative 3x in the middle. So it's going to have to be what I had before. Now I have 6x and 1x. 6x and 1x, that's weird. That doesn't factor either, right? So really we can't factor this. Okay, so what am I going to do if this is not factorable? I'm going to do the quadratic formula, right? We know that a is 3, b is negative 3, and c is 2. Okay, so let's go ahead and do this. Here we go. X equals negative b, opposite b would be positive 3, plus or minus square root b squared, we have negative 3 squared, minus 4ac, a is 3, c is 2, all over 2a, and a is 3. Okay, so let's simplify that. We get x equals 3 plus or minus the square root of 9. This would be negative 12 times 2, which is negative 24 over 6. So we get 3 plus or minus. What's 9 minus 24? 9 minus 24 is going to give me negative 15 underneath that root over 6. And I'm just going to stop there. Because as soon as I see a negative under the root, what kind of solutions am I going to have? Imaginary, right? This would be I radical 15 over 6. So there's no real solution. So am I going to see any intersection points? No. Okay, no intersections on the graph. Okay, no real solutions there. If you wanted to check this in your graphing calculator, remember we just have to get it in a friendly calculator form where we have y equals. So like here, if I rewrote this and I added y to both sides, I would get 2x squared minus 5x equals y minus 2. And if I added 2 to both sides, we get 2x squared minus 5x plus 2 equals y. I could put this in y1. Okay, get this in a calculator-friendly form as well by subtracting y on both sides. We would get that x squared plus 2x equals negative y. And then we could divide everything by negative 1. So we'd have negative x squared minus 2x equals y. Put that in your y2, and let's see if we have any solutions here. 2x squared, I'm just going to y equals on my calculator. I'm putting in 2x squared minus 5x plus 2 in y1. And then in y2, I'm putting negative x squared minus 2x. Okay, let me switch over to my graphing calculator so you can see it. All right, let me go back to my y equals form. You can see I just put these in my y1 and y2. And when I graphed it, do you see how there's no intersection? Okay, that's because we had imaginary solutions. All right. So we talked about parabolas. Some nonlinear systems can have equations of this form as well. That is a circle, right? So if I have something like this, let me write it out with my marker. You have x squared plus y squared equals 16. That would be a circle where the radius is 4. And how I get the radius is I just take this number 16 and I find the square root of it. Okay, remember this is r squared, so in order to get r, we would take the square root of whatever that number is to get the radius. Okay, this is going to be a circle. The equation is standard form of a circle with center 0, 0 and radius r. So again, we can have no solution if there's no intersections, one real solution if there's one intersection, or two solutions. Okay, so it says solve the system by substitution. I'm just going to take negative 3x plus 10, and I'm going to plug it directly in for y up here. Okay, so what does that look like? That's going to give us x squared plus y, negative 3x plus 10 squared equals 10. Okay, and this is going to be something that we're going to have to expand out. Right, this is really going to be x squared plus negative 3x plus 10 times negative 3x plus 10 equals 10. Let's FOIL. This will be 9x squared minus 30x minus 30x plus 100 equals 10. Combine like terms. We've got 10x squared. This is going to be minus 60x plus 100 equals 10. And look at what we have. We have a quadratic equation. So I'm going to subtract 10 from both sides so that we can get this set equal to 0. Look for a GCF. So is there a GCF? There is. All terms are divisible by 10. So if I divide each one of these terms by 10, we would get x squared minus 6x plus 9. Okay, let's factor that. This is actually going to be a perfect square trinomial. We have x times x is x squared, 3 times 3 is 9, and both of these must be negative in order to get a negative 6x in the middle. And so set that x minus 3, set both of those x minus 3's equal to 0 and solve. We're going to get the same thing, right? X equals 3 in both situations. So if x is 3, then what is y? Well, remember that y was equal to negative 3x plus 10. So if I plug in 3 for x, we can get what y is equivalent to. That's going to end up being 1. So our intersection point, or our answer, is going to be when x was 3, our y output was 1. And we should expect to see one intersection point at 3, 1. Okay. Okay, let's go ahead and go down here. Just more practice with solving nonlinear systems. In this case, we've got a circle, right? And y equals negative 6 would be a horizontal line through the y value negative 6. We want to know where they intersect. So I'm just going to plug in negative 6 for y. So I get x squared plus 36 equals 64. If we subtract 36 on both sides, we get that x squared is 28. Right, square root both sides, and don't forget your plus or minus. We have to simplify the square root of 28. Let's list our perfect squares. We have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. And 28 would fall in between 25 and 36. It is not divisible by 25. It is not divisible by 16. Is 28 divisible by 9? No. Is 28 divisible by 4? Yeah, 4 times 7 would be 28. So I'm going to break this into the square root of 4 times the square root of 7. Then we can simplify the square root of 4 because it's perfect down to 2. Okay, so we get plus or minus 2 radical 7, which is really 2x values, right? We've got 2 radical 7 and we've got negative 2 radical 7. And we still have to find y. Well, that's easy peasy. Y is already equal to negative 6. So we can write our 2 ordered pairs that are our solutions. When x is 2 radical 7, or 2 root 7, y is negative 6. And when x is negative 2 square root 7, y is negative 6. Okay, so those would be our 2 points of intersection. Now let's go over here. Right here we've got a parabola and, again, a horizontal line. So let's find out their intersection. I'm going to plug in 6 for y. I'm going to solve for x. So in order to do that, I'm going to add 3 on both sides. We get 9 equals x plus 2 squared, right? We wanted to isolate the squared term. Now we can square root both sides. So we get plus or minus 3 equals x plus 2. Right? These are inverse operations, so they undo each other. The square root undoes the squaring. And we've got to get x by itself. So I'd have negative 2 plus or minus 3 equals x, which is really two different values for x. We have negative 2 plus 3, which is 1. And we would have negative 2 minus 3, which is negative 5 for x. Okay, so we get that x is 1, and we get that x is negative 5. And I have to figure out what y is. Well, remember, up here it gave us that y was 6. So we have 2 ordered pairs as our answer. We have 1, 6 as an answer. And then we've got negative 5, 6 as an answer. Those would be our 2 points of intersection.